Hi, in this video, I'll be going through a more general type of boundary value problem, and for this eigenvalue problem will be known as a Sturm-Liouville boundary value problem. And the Sturm-Liouville boundary value problem will be of the form here. So you can write it in this form, and the boundary conditions are homogeneous and separated. Boundary conditions are said to be separated if they involve only one boundary per equation. So you can see from the first one, it only involves alpha, and the second one only involves beta. In this case, the previous time we seen that the eigenvalue problem, the basic one, which is y double prime plus lambda y equals to 0, is already in Sturm-Liouville form. Then, now, if we just take this one over here, we actually can see that it is not in the form that we want, because we will be unable to write it in terms of this. But the good news is we can now convert a general problem into a Sturm-Liouville form by choosing a suitable integrating factor. So let's introduce some notations first, and we let this be the linear operator for such a eigenvalue problem. And the differential equation can now be written as this linear operator equals to lambda rx y. So how do we convert an eigenvalue problem into a Sturm-Liouville one? Well, if we take a general eigenvalue problem, then we want to convert it into this form. We just need to compare coefficients. So we multiply a integrating factor and then we compare. Okay, so we compare it, and then we actually see that our mu x, our function mu, must equals to e integral of b over a at dx. So b is this, a is this. Then the equation would then become this form. So if you want to find, now we see an example, so we don't need to really memorize it. You just need to multiply the equation, compare it with the Sturm-Liouville form, and then we actually can see what we want. We want the ux to equals to px and minus 2ux equals to p prime x. And with that, we are able to solve for mu, which is this. So we just set the c equals to 1, because any constant multiple will work. Then the integral will be this, and as such, we get this equation, which will then be now in Sturm-Liouville form. And so we got some theorems, and one theorem is we will sure show that the linear operator for this a boundary value problem is self-adjoint. And self-adjoint just means that the inner product of LU comma V equals to inner product of U comma LV. So the linear operator can shift between the parameters. So because of that, to prove that L is self-adjoint, we just let LUV, and we just write it out, and then we use the integration by parts to get the following over here. And then we write ULV and we see this. Okay, so we got this already, and we want to show that they are equal. Well, what we can just do is we take one minus the other, and we actually arrive to this equation. So to prove that this is 0, we just need to apply the boundary conditions, because you sub in the alpha and beta. So we just need to show this following step equals to 0. And using the idea that, so we just sub in the alpha, and then we actually can show that it equals to 0. And if this And if the A1 is now not equals to 0, then it immediately shows that it is 0. So this shows that this equation over here equals to 0 because this expression here is 0. Then means that the two inner products are equal, and this shows that the linear operator is self-adjoint. So that is how you show that the linear operator is self-adjoint. And why do we care so much about it being self-adjoint? Well, now let's look at one thing. Now let's look at a more specific case known as the regular Sturm-Liouville problem. And in this case now, we just restrict the R and the P functions to be positive. And this is known as the regular Sturm-Liouville problem. So our first eigenvalue problem is of course regular. Our second one is regular because e to the power of something is always positive. And the good news is that once you know that it's the regular Sturm-Liouville problem, you have many properties for its eigenvalue and eigenfunction. And one property is that all its eigenvalues must be real. So how do we do something like this is, okay, let lambda be an eigenvalue, and we already know L is self-adjoint, so this equation holds. Once you have this equation, we can find the inner product, and then we bring over to the other side, we minus off, we actually get this. But we know because it's a regular Sturm-Liouville problem, this Rx is positive, y squared is positive, so this whole integral will always be positive, which means for this to equals to 0, lambda must equals to lambda conjugate. So for lambda to equal to lambda conjugate, lambda must be real. So that's how you so that's the nice thing about the regular Sturm-Liouville problem. While in other boundary value problems, you know that the eigenvalues can take on real or complex, but in this case, the eigenvalues must be real. And then a few other properties is that the sign of the eigenvalues is, so the once you know that it's real, we also can tell that the lambdas must be positive, cannot be negative. So you just take the inner product of Ly with y itself. So this we product with y, and then we actually get this. So it's a standard trick that we have already seen in the previous video. You just always take the inner product with the function itself, and so this allows us to pull out the lambda, but you keep the y squared. So you know this whole portion again is positive. So if the thing is positive, then we just need to find the left hand side, and the left hand side can be just using the we can expand now to get this following form. Okay, so now you see this part, the sign depends on Q, and this part is larger than 0 because it's positive, and for this boundary term, then there will be a boundary term. So to determine the sign of the eigenvalues, if we know that this, because okay, so this side is positive, so we can just divide over. So the sign really only depends if we already know this is positive and we know the boundary term is larger or equals to 0 depending on the boundary condition, then we should be able to tell that the lambda is positive because this whole portion here will be positive. So an example would be the previous time where we got this eigenvalue problem, and actually we can see that the boundary term of this inner product is 0. So lambda will be this integral over the other, so this positive and this positive, so the lambda must be positive. And lambda can only equal to 0 if the following happens. But for this to happen, then lambda must be constant and it must be 0. So this shows that lambda is strictly positive since if lambda is 0, then the eigenfunction is trivial, which cannot be. Another property that we can do is we actually see that the eigenfunctions corresponding to different eigenvalues are orthogonal to each other, meaning they satisfy the following equation. So to prove of the orthogonality, it is very similar. So you got two eigenfunctions, you just take the linear operator and then you take the inner product. So it's the linear operator of Lm comma sin phi n, then it's equal self-adjoint, so you can just bring the linear operator to the other side and then we expand out and we should get that so because they are different eigenvalues, so this part is non-zero, meaning the inner product must be 0. So that means that they are orthogonal to each other. And the last property we have is that every eigenvalue there is only one eigenfunction, and you can actually arrange them in a order from in strictly increasing function. But this is a bit out of our video because it's a bit longer and a bit more tedious. So just to prove that it's simple, we again use we should show how we're using the standard techniques. So the standard techniques is that if you have two eigenfunctions, you want to show that they are linearly dependent, meaning the width constant between them is 0. So because you know phi 1 and phi 2 satisfy the same boundary condition, you have the following equations over here, and because of this we can write in matrix form over here. So we want to show this the 0 matrix, so we just need to find the determinant. And how do we do that? Well, because this is a non-zero vector, then this must be 0, so the matrix is a singular one. This means that the determinant between them is 0, which implies this. So because the Wronskian is just this determinant, and we already showed that it is 0, then by Abel's theorem is always 0. So the phi 1 and phi 2 are linearly dependent. So it's relatively simple to show that the eigenvalues are simple. So you see how now we have proved the properties of a regular Sturm-Liouville problem, and I hope you have understood more about boundary value problems. So that's all for this video. I hope you have enjoyed it. If I have any other videos, I'll post them in this playlist, and feel free to like, share and subscribe, and I'll catch you in the next one. Bye.